All right, Math 192, folks. Activity 30 here. We're going to talk about continuing our talk on counting principles. We're going to throw some probability into it as well. So let's start off with some problems about arranging letters or from a word. So the first problem in the activity says, in how many ways can the letters to the word bacterium be arranged? Okay, so how many letters are in the word bacterium? 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And are there any repeated letters? B, A, C, T, E, R, I, U, M. No repeated letters. Okay, so no repeated letters means it's straight up very similar to what we did last week. We have 9 spots. 2, 3, 4, 5, 6, 7, 8, 9. The first letter choice, we have 9 choices, 8 choices, 7, 6, 5, 4, 3, 2, and 1. That's the same thing as 9 factorial, which is calculator math. We're going to type in the number 9 and hit math, go over to the probability, and then option 4 for the factorial. And 362,880. Okay. So 9 letters, and your explanation is showing me that setup and what's going on there. Okay, how many arrangements begin with a consonant? All right, so again, we've got 9 spaces that we're going to arrange, and we're going to begin with a consonant. Okay, so consonants are letters that aren't vowels. So that's the B, C, T, R, and M. So 1, 2, 3, 4, 5 choices for the first space. And then if we choose one of those, how many choices are there for the second space? There are 8. 7 for the third. 6, 5, 4, 3, 2, 1. This is the same thing as 5 times 8 factorial. So calculate them 5 times math, probability, option 4. Didn't type my 8 first. Probability, option 4. 201,600. Okay. Option C, or part C here, says, okay, let's throw some probability into it. So we're going to mix in that counting principle with probability. Our probability that it asks for, here's the probability of one of the arrangements in part A beginning with a consonant. So we have 201,600 that will begin with a consonant, and then we have 362,880 possible arrangements in total. So this is, again, successes over possible ways. So we're going to reduce that fraction. So with my calculator here, I'm going to grab my 201,600 divided by the 362,880. Enter, and we get a decimal for that. I'm going to hit math, enter to change it to 5/9. That's the reduced form of that fraction. The decimal equivalent for that is 0.5 with the 5 repeating out of that. So the simplified fraction and then the decimal equivalent approximation for that. So if it's a repeating decimal, use the bar notation to indicate that. All right. D part asking how many ways can these letters be arranged if the arrangement must end in a vowel. Okay, so we still have 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. But we're going to end in a vowel this time. So the word bacterium, you have the A, E, I, and U. That's 4 possibilities to end with. there. Well, if we're ending with the vowel, so we're choosing one of the vowels at the end, then that means we only have 8 choices at the front. 7, 6, 5, 4, 3, 2, 1. So this is 8 factorial times 4. Get that. So 8 math probability factorial times 4, 161,280. Again, the setup with the spaces and the counting principle, there's plenty of explanation for me. All right, let's continue that on the next page. How many ways can these letters be arranged if the arrangement must begin with a consonant and end with a vowel? So when we're looking at that one, we've got, again, the 9 spaces. Consonants, there are 5, 4 vowels at the end. So if we choose a consonant at the front and a vowel at the end, that's taking away 2 of the letters. There's only 7 to deal with. 6, 5, 4, 3, 2, 1. So it's 4 times 5 times 7 factorial is what we really end up with here. So 4 times 5 times 7 factorial, 100,800. Okay. And then what is the probability of one of the arrangements in part A begins with the consonant or ends with a vowel? Probability, again, we're going to be over our original number of ways, which was 362,880 possible ways. So we're dealing with probability again. Possible ways goes on the bottom. And then on top, we've got to find out the arrangements that begin with a consonant. So we add up those that begin with a consonant were the 201,600. So this is begin with consonant. Plus those that begin with or end with a vowel, which was 100,000 or 161,280, and with a vowel. But then we've got to take into account those that do both of those things and make sure we don't count something more than once. So we're going to subtract away the 100,800 that do both. Okay. We do that. That's going to give us 262,080 over 362,880. All right, so we'll show that math there. 201,600 plus 161,280 minus 100,800, and then divide that by 362,880, which was our possible ways to arrange that. And I'm going to get the decimal equivalent, and the reduced fraction is 13 over 18, which is the decimal is 0.7 with the 2 repeating. Again, using that bar notation to show that decimal there. Not rounding there, but showing the bar notation. If it doesn't have a repeating decimal, let's round to 2 decimal places will be fine. How many ways can these letters be arranged if the word trace must appear in there? So the word trace being in there. So if that's the case, let's just take our 9 spots. And let's put the word trace at the beginning. Trace. And then how many letters does that leave? Well, that's used up 5 of them. So it leaves 4, 3, 2, and 1. But here's the problem is trace could be at the beginning or it could be here in between the four choice, in between the first letter and the next letter that's not in the word trace. Or it could be there, or it could be there, or it could be at the very end. So that's 1, 2, 3, 4, 5 places that it could, extra places that it could be in there. So we've got 4 factorial plus the 5 other places that it could be. So 4 factorials, 4 times 3 times 2, which is 24 plus 5. So it's a little quicker to do that without the calculator. There are 29 ways out there. Okay. H, similar problem. It says, what's probability one of the arrangements in part A has the word mice in it. And so G was just number of ways. H is a probability problem. So we're going to have to find the number of ways that mice could appear and then also figure in what's the probability of that. So again, 9 blanks. And if the word mice is there, if it's at the beginning, that's one of the ways. And then you have 4 letters, there's 5 left. Letters are 5 factorial for the 5 letters that are not used yet. And then we're going to look at, okay, well, that could be at the beginning. That's one way. It could be between those two. That's the second way, third way, fourth way, fifth way, sixth way that it could be. So we've got 5 factorial plus 6 more ways that it would be. 5 factorial is 5 times 4 times 3 times 2 times 1. So it's 5 times 4 is 20 times 3 is 60 times 2 is 120 plus 6 is 126 ways. Probability would be 126 over 362,880. That was our original number of ways that it could happen. I'm going to use the calculator to help me reduce that. 362,880. Math, enter. 1 out of 200 or 2,880, which is a decimal. We're going to have to approximate here. Going 4 decimals, so it's 0.00347. We'll do 347.2 repeating there. We'll just go ahead and go all the way out there. You want the reduced fraction and then that decimal there. Let's just get it all the way to that to show that that's what's happening because it did repeat for us. All right. Let's look at number 2 here. A little tougher problem here because you got to build our sample space that we've got here. So we've got a kind of a new game here with a different kind of a deck of cards. So this deck of cards has 8 red cards, 3 blue cards, 4 green cards, and 5 yellow cards. That's 20 cards total. And what we're doing is we're drawing a card without replacement. Okay, so from a special deck, we're drawing 2 cards. So 2 cards without replacement. So we shuffle it, pick 2 cards. That's the hand, basically. All right. So in the following table that lists the 16 possible outcomes for this experiment using R for red, B for blue, Y for yellow, and G for green. And we want to also list the number of ways that outcome could happen. Okay. So we started out here with R, which means red card, red card. When you draw your 2, well, how many red cards are there? Well, there are 8 red cards in the set that were described to us. So we have 8 reds, 3 blue, 4 green, and 5 yellow. Okay, just so we know You don't have to scroll back and forth there. So 8 reds. So when we draw that first card, there are 8 reds to choose from. And that second card, there's only 7 reds to choose from. So there's 56 ways that that can happen. Okay. If we draw a red, then a blue, there's 8 reds, 3 blues, which is going to give us 24 ways that that can happen. Red, green, we got 8 reds and 4 greens. 8 times 4 is 32. Red, yellow, 8 times 5 is 40 ways. Okay. Well, the next way, it doesn't matter which way we go here. I'm just going to go blue next. If the first card we draw is a blue, then we could do blue, red. We could do blue, 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 green, and blue, yellow. Okay, so the first card we draw is blue. You have the other 4 options that we can do. So blue, red would be 3 times 8. It's 24 ways that that can happen. Blue, boo, we have 3 blue cards to begin with, but if we take one of them out, there's only 2 left, so it's 3 times 2. There's only 6 ways that we could draw blue, blue. Blue, green, you got 3 times 4 is 12. Blue, yellow would be 3 times 5 is 15. Okay, the next outcome that could happen, let's say we drew the green card first. Green, red, green, blue, green, green, and green, yellow. Okay, green, red, 4 times 8 is 32 ways. Green, blue, 4 times 3 is 12 ways. Green, green could be 4 times 3, which is 12. Green, yellow would be 4 times 5 is 20. And then the last way would be yellow, red, yellow, blue, yellow, green, yellow, yellow. Okay, yellow, red, 5 times 8 is 40. So 5 times 3 is 15. 5 times 4 is 20. And yellow, yellow would be 5 times 4, which is 20 as well. Okay, we've got our data set here, sample space to deal with. What's the probability of getting red, blue as an outcome? Okay. Okay. So how many different 2-card hands are there? Well, there are 20 cards to begin with. Okay. So total hands would be 20 for the first one. Without replacement, be 20 times 19. 20 times 19. Know my 19 times tables. 380 total 2-card hands. Okay. And it wants to know red, blue. So we go up here to our chart. We find red, blue. There are 24 of those. And again, it's specifically red, blue, not blue, red. They're not the same thing. Okay. And so 24 over 380, we're going to use will help to reduce that. There's my decimal approximation. I want to get the fraction. So math, enter, 6 over 95. And a decimal approximation for that, 0.0. Let's go 3 decimal places, 0.063. I think 3 decimal places would be the best for us to do there. What's the probability of getting 2 cards that are the same color as an outcome? Okay, so two cards the same color. So that could be red, red. It could be blue, blue. Could be green, green, or yellow, yellow. So we've got 4 different things that happens with. So we have red, reds, blue, blues, green, greens, and yellow, yellows. You need to add all those together. So 56 plus 6 is, I'm just going to write those down. 56 plus 6 plus 12 plus 20. 12 is right for green, green, yes. And out of the 380 possible 2-card hands. So again, in your explanation, it might be good to write somewhere that is red, red, blue, blue, green, green, yellow, yellow. Maybe that's a good way to say that. So we're going to add these things up. So 56 and 6 would be 62, and 12 would be 74, and 20 would be 94 out of 380. And we're going to reduce that with a little help. Math, enter. 47 out of 190. Decimal approximation for that is going to be 0.247, or 3 decimal places again. And there we have the reduced fraction and the decimal approximation for that. All right. D, what is the probability of getting 2 cards that are different colors as an outcome? Okay. So we know what's the probability of getting cards that are the same color. That means everything else is cards of different colors. So if we just take 380 minus 94, this is same colors, then that will get us how many hands have different colors in them. Doesn't matter what kind of colors they have, but they're different colors. They're not the same color for the 2 cards. Okay, so 380 minus 94, 286 over 380. Enter 143 over 190. 0.753. What is the probability that the outcome will include at least 1 blue card? Okay, well, when you see the word at least, one of the best things you can do to find the probabilities of that is take the complement of that. So what's the complement of at least 1 blue? That's absolutely no blues. Okay, so let's find the hands with no blue. Okay, hands with no blue are 56, 32, 40. None of these. So 56 and 32 be 88 plus 40. It'd be 128 plus 32. So 56, 32, 40. We'll add those up. 56, 32, 40 plus 32, 12, 20. Plus yellow hand first, so 40, 20, 20. Adding all of those up is what we're going to do there. Okay. Space here. All right, so let's add those up. 56. So yeah, I've got 40, 20, 20. That's 80. And another 20 is 100. 140. 172. 184. 186 plus 30. 216. And 216 plus 56. 272 hands that have no blue. So that means how many hands have blue? 380 minus 272 over 380. So we're getting probability here. So 380 minus 272 divided by 380. Math in Enter, get the reduced fraction, 27 over 95. Decimal approximation. Again, go in 3 places, 0.284. All right. So probability can get a little confusing, but it's all about counting how many possible things you've got. And then sometimes it's counting the opposite of that, when at least that's the easiest way to do that, I think. Or you could count it, you could have counted up the 27 hands that had blue in them if you wanted to. It works the same way, it gets you those same results. Okay, so activity 30, counting principal probability.